For years, astronomers peered into the chaotic heart of Beta Pictoris, a system so studied it's practically a cosmic textbook, only to find a baffling mystery: a massive planet eluding detection, cloaked by a swirling disk of dust so thick it swallowed all light. Until now. The James Webb Space Telescope didn't just pierce that veil, it rewrote the rules. By tracing the faint fingerprints of carbon monoxide, water vapor, and methane in the planet's atmosphere, Webb uncovered a gas giant twice Jupiter's size, orbiting perilously close to its star. This isn't just a discovery, it's a breakthrough. For the first time, we've glimpsed a hidden world in a system we thought we understood, proving that even the most scrutinized corners of the universe still hold secrets waiting to be uncovered. And this method? It could revolutionize how we hunt for exoplanets, ones that might one day hold the keys to life beyond Earth. In the vast expanse of our galaxy, where stars are born and planets take shape, one system has long captivated astronomers: Beta Pictoris. For decades, this young star and its surrounding disk of cosmic dust have been a laboratory for studying planetary formation. Now, a groundbreaking discovery has rewritten our understanding of this system. A massive planet, hidden in plain sight, has been revealed by NASA's James Webb Space Telescope. This planet, named Beta Pictoris d, is not just another distant world, it's a milestone in the search for exoplanets, proving that even in the most studied systems, surprises await. Let's explore how this discovery was made and why it matters for the future of astronomy. Beta Pictoris is a star only slightly younger than our Sun, located about 63 light-years away. Around it, a swirling disk of dust and gas has been observed for decades, a remnant of the planet-forming material that once surrounded our own Sunday. This disk, however, has also been a puzzle. While astronomers have detected several planets in the system, most notably Beta Pictoris b, a gas giant discovered in the 1980s, the presence of a second planet remained elusive. For years, observations suggested something was missing, a shadow in the data that hinted at an unseen world. The breakthrough came when the James Webb Space Telescope, with its unparalleled sensitivity and ability to peer through cosmic dust, turned its gaze toward Beta Pictoris. What Webb found was unexpected: a planet, hidden within the dusty disk, had been there all along. But how did scientists detect it if it was invisible to traditional methods? The answer lies in the planet's atmosphere. Unlike the massive planets we see in our solar system, which are too distant to observe directly, Beta Pictoris d is shrouded in a thick veil of dust. Yet, its presence was betrayed by the faint traces of gases it emits. By analyzing the light from the star and the surrounding disk, Webb's instruments detected subtle signatures of carbon monoxide, water vapor, and methane, chemical fingerprints that reveal the composition of a planet's atmosphere. This method is revolutionary. For years, astronomers have relied on indirect techniques to find exoplanets, such as detecting the dimming of a star as a planet passes in front of it or measuring the gravitational tug a planet exerts on its host star. These methods work well for planets that are close to their stars or large enough to cause noticeable wobbles. But planets like Beta Pictoris d, massive, distant, and veiled in dust, are notoriously difficult to spot. The new approach, however, offers a promising alternative. By studying the light that passes through or is emitted by a planet's atmosphere, scientists can infer its presence and even its chemical makeup. This discovery demonstrates that such methods can uncover planets and systems where traditional techniques fall short, opening new avenues for exoplanet research. The significance of Beta Pictoris d extends beyond its discovery. It provides a rare opportunity to study a planet in its formative years. Beta Pictoris is a young star, only about 20 million years old, meaning the planets around it are still in the early stages of their evolution. This makes the system a unique laboratory for understanding how planets form and develop. By analyzing the atmosphere of Beta Pictoris d, scientists can gain insights into the processes that shape gas giants, how they accrete material, how their atmospheres evolve, and what conditions might exist on such worlds. These insights could also shed light on the early history of our own solar system, where similar processes may have occurred. But the discovery of Beta Pictoris d also raises intriguing questions. For instance, how did this planet end up in its current position? The disk around Beta Pictoris is vast, spanning hundreds of astronomical units, far beyond the orbit of Pluto in our solar system. The presence of a planet in such a distant region challenges existing models of planetary migration. Some theories suggest that planets can form in these outer regions and remain there, while others propose that they migrate inward over time. The existence of Beta Pictoris d adds complexity to this debate, suggesting that planetary systems may be more dynamic and diverse than previously thought. Another mystery is the nature of the dust disk itself. While the disk has been observed for decades, its structure and composition have remained enigmatic. The discovery of Beta Pictoris d implies that the disk is not just a passive remnant of planet formation but an active environment where planets interact with their surroundings. The planet's gravitational influence may shape the disk, creating gaps or stirring up material that could lead to the formation of additional planets. Studying these interactions could help astronomers better understand the complex dance of forces at play in young planetary systems. The detection of Beta Pictoris d also highlights the power of the James Webb Space Telescope. Unlike its predecessors, Webb's advanced instruments allow scientists to peer into the infrared spectrum, where the faint glow of planetary atmospheres becomes detectable. The telescope's ability to resolve fine details and distinguish between the light from a star and the light reflected or emitted by a planet is a game-changer. This capability is especially crucial for studying planets in dusty environments, where traditional optical telescopes struggle to penetrate the veil of dust. Webb's success in this case underscores its role as a transformative tool for exoplanet research. For the broader field of astronomy, this discovery represents a paradigm shift. It demonstrates that planets can be found in systems where they were previously thought to be invisible, expanding the scope of what we can observe. This method of detecting planets through atmospheric signatures could be applied to other systems, potentially uncovering more elusive worlds. In particular, it may help astronomers identify planets in the habitable zones of their stars, those that could potentially support life. While Beta Pictoris d is a gas giant, the techniques used to study its atmosphere could one day be adapted to analyze smaller, Earth-like planets, offering a glimpse into their potential to sustain life. The journey to discover Beta Pictoris d also reflects the collaborative and iterative nature of scientific discovery. For years, astronomers have studied this system, piecing together clues from decades of observations. The discovery of this planet was not a sudden revelation but the culmination of persistent curiosity and technological advancement. It reminds us that even in the most thoroughly explored systems, there is always more to learn. The history of astronomy is filled with such moments, when what was once thought to be the end of the story becomes the beginning of a new chapter. As we look to the future, the study of Beta Pictoris d and similar systems will continue to shape our understanding of planetary formation and the diversity of worlds in the universe. The James Webb Space Telescope has already revolutionized our ability to explore distant planets, and this discovery is just one example of its potential. With each new finding, we come closer to answering fundamental questions about our place in the cosmos. How do planets form? What conditions allow life to emerge? And how common are worlds like our own? The search for answers continues, driven by the same wonder that has inspired astronomers for centuries. For decades, the Beta Pictoris system has been a cornerstone of exoplanet research, a star surrounded by a swirling disk of dust and gas, a cosmic nursery where planets are thought to form. Yet, despite years of observation, one mystery persisted: a massive planet, hidden behind the thick veil of dust, eluded detection. Now, NASA's James Webb Space Telescope has solved this enigma, revealing a world that had been invisible to all previous instruments. But how did scientists finally uncover this hidden giant? The answer lies in a combination of cutting-edge technology, decades of observation, and a breakthrough in how we search for planets beyond our solar system. The journey began with the James Webb Space Telescope itself, launched in 2021 as the most powerful observatory ever built. Unlike its predecessors, Webb operates primarily in the infrared spectrum, allowing it to peer through cosmic dust that has long blocked our view of planetary systems like Beta Pictoris. This system, located about 63 light-years from Earth, has been studied extensively since the 1980s. Early observations with ground-based telescopes and the Hubble Space Telescope revealed a disk of debris orbiting the young star, but no planet could be confirmed. The disk's brightness made it nearly impossible to detect a planet embedded within it until Webb arrived. The key to this discovery was not a direct image of the planet, but rather the subtle fingerprints of its atmosphere. Scientists used Webb's near-infrared spectrograph, NIRSpec, and mid-infrared instrument, MIRI, to analyze the light passing through the dust disk. These instruments split the light into its component wavelengths, revealing the unique spectral signatures of molecules present in the planet's atmosphere. The breakthrough came when researchers detected three key gases: carbon monoxide, water vapor, and methane. These molecules are not typically found in the cold, dusty environment of a debris disk, but their presence strongly suggests a planet, specifically, a massive gas giant absorbing and emitting radiation from its host star. This method, known as transmission spectroscopy, is not new, but its application to a system like Beta Pictoris was groundbreaking. In most exoplanet studies, scientists observe planets as they pass in front of their stars, measuring how starlight dims and shifts. However, in Beta Pictoris, the planet's position within the dust disk made this approach impractical. Instead, the team used a different strategy. They analyzed the light that had passed through the disk, searching for the faint spectral signatures of molecules trapped in the planet's atmosphere. The challenge was immense. The disk itself emits light, masking the planet's signal, and the gases detected had to be identified with extreme precision. Yet, Webb's advanced instruments and the team's meticulous analysis allowed them to isolate these molecular signatures, confirming the presence of a planet. The process took years of preparation and collaboration. For decades, astronomers had studied Beta Pictoris, accumulating data on the disk's composition and dynamics. This historical context was crucial. By comparing Webb's findings with earlier observations, scientists could rule out alternative explanations for the detected gases. For instance, carbon monoxide could originate from the disk itself, but its abundance and distribution pointed to a planetary source. Similarly, methane and water vapor are more commonly associated with planetary atmospheres than with interstellar dust. The combination of these molecules created a compelling case for a hidden planet, but confirmation required more than just detection. It demanded a deeper understanding of the system's evolution. To validate their findings, the team turned to computational models. They simulated how a massive planet might interact with the dust disk, predicting the distribution of gases and the planet's orbital characteristics. These models aligned remarkably well with the data collected by Webb. The planet's mass, estimated to be several times that of Jupiter, matched predictions based on the disk's dynamics. Its location, roughly 1.5 times the distance between Earth and the Sun, placed it in a region where such a planet could form and remain stable. The models also suggested that the planet's gravity was shaping the disk, creating the observed structures. This synergy between observation and theory provided strong evidence for the planet's existence, even without a direct image. The discovery also relied on the unique capabilities of Webb's instruments. Unlike earlier telescopes, which struggled to penetrate the dust, Webb's infrared sensors could detect the faint heat signatures of the planet. The planet's atmosphere, warmed by the star's radiation, emitted infrared light that Webb could capture. This light, combined with the spectral analysis of the gases, allowed scientists to infer the planet's temperature, composition, and even its atmospheric dynamics. The presence of methane, for example, hinted at complex chemical processes occurring in the planet's upper atmosphere, while water vapor suggested the presence of ice clouds or high-altitude layers. These details, though indirect, painted a vivid picture of a distant world. The timeline of this discovery is as much a story of patience as it is of technological triumph. The first hints of the planet's existence emerged in 2023, when initial data from Webb's instruments revealed anomalies in the disk's light. Over the next few years, the team refined their analysis, cross-referencing their findings with decades of prior data. By 2026, the evidence had grown so compelling that the discovery was announced. This process underscores the importance of long-term observation in astronomy. The Beta Pictoris system had been a focal point for over 40 years, and its study provided the foundation for Webb's breakthrough. Without this historical context, the detection of the planet would have been far more challenging. What makes this discovery so significant is its implications for future exoplanet research. The method used here, detecting atmospheric gases in a dusty disk, could be applied to other systems where planets are obscured by debris. This opens new avenues for finding elusive worlds, particularly in young planetary systems where planets are still forming. The presence of methane and water vapor also raises intriguing questions about the planet's potential for hosting life, though such speculation is speculative. What is clear is that this planet, now named Beta Pictoris d, represents a new frontier in our understanding of planetary formation and evolution. As scientists continue to analyze the data, they are uncovering more details about this hidden world. The planet's orbit, its interaction with the dust disk, and the composition of its atmosphere all provide clues about how planetary systems evolve. These insights could help answer fundamental questions about the formation of our own solar system and the diversity of worlds beyond it. The discovery of Beta Pictoris d is not just a triumph of technology, it is a testament to the power of human curiosity and the relentless pursuit of knowledge. In the vastness of space, where planets hide behind cosmic veils, the James Webb Space Telescope has shown us that even the most elusive worlds can be found, one spectral signature at a time. For decades, astronomers have marveled at the Beta Pictoris system, a young star surrounded by a swirling disk of cosmic dust and gas, a celestial nursery where planets are still taking shape. This system, just 120 light-years away, has long been a proving ground for exoplanet research, home to at least one confirmed planet, Beta Pictoris b, and a vast, glowing debris disk that has hidden its secrets from view. But now, a new discovery has upended our understanding of this system. A massive, previously unseen planet, Beta Pictoris d, has been detected lurking behind the dust, its presence revealed not by direct imaging but by the faint fingerprints of its atmosphere. This breakthrough, made possible by NASA's James Webb Space Telescope, is more than just a catalog entry, it's a revolution in how we search for planets in the cosmos. Let's dive into the science behind this discovery and why it matters for our quest to understand the universe. At the heart of this revelation is a technique that has quietly transformed exoplanet detection: spectroscopy. When light from a star passes through a planet's atmosphere, certain wavelengths are absorbed or emitted, creating a unique pattern of dark or bright lines in the spectrum. These lines act like a fingerprint, revealing the chemical composition of the atmosphere. For years, astronomers have used this method to study planets orbiting other stars, but it has always been a challenge. Most exoplanets are too faint, too distant, or too shrouded by stellar light to detect these subtle signals. The Beta Pictoris system, however, presented a different kind of puzzle. The planet's presence was masked by a thick disk of dust and gas, a swirling halo of debris that has long obscured its view. Yet, the James Webb Telescope, with its advanced spectroscopic capabilities, has now pierced through this veil, uncovering the planet's atmospheric signature. The key to this discovery lies in the molecules themselves. Scientists detected traces of carbon monoxide, water vapor, and methane in the light from Beta Pictoris d. These molecules are not random, they are the byproducts of a planet's atmosphere, shaped by its temperature, pressure, and chemical processes. Carbon monoxide, for instance, is a telltale sign of a planet that has undergone significant internal heating, while water vapor and methane hint at the presence of complex chemistry, potentially even the building blocks of life. The detection of these molecules is not just a technical triumph, it's a glimpse into the planet's history and environment. By analyzing their abundance and distribution, astronomers can infer the planet's age, its atmospheric dynamics, and even the processes that might have shaped its formation. This level of detail is rare in exoplanet studies, where most observations are limited to basic characteristics like mass and orbit. But why is this method so groundbreaking? For years, the search for exoplanets has relied on indirect techniques. The transit method, for example, detects planets by measuring the dimming of a star as a planet passes in front of it, while the radial velocity method uses the wobble of a star to infer the presence of an orbiting planet. These methods have been incredibly successful, but they come with limitations. They are most effective for large, close-orbiting planets, often those that are hot and dense, like the gas giants in our own solar system. Smaller, colder planets, especially those in the habitable zone, remain elusive. The discovery of Beta Pictoris d, however, demonstrates a new way to find planets that might have been overlooked. By focusing on atmospheric signatures, astronomers can detect planets even when they are hidden behind dust, or when their light is too faint to be seen directly. This method opens the door to a new class of exoplanets, those that may have formed in different environments, or that have unique atmospheric compositions that defy traditional detection methods. The significance of this discovery extends beyond the Beta Pict system. It challenges our assumptions about how planets form and evolve. The Beta Pictoris system is only about 20 million years old, a mere blink of an eye in cosmic terms. In such a young system, planets are still in the process of settling into their orbits, and their atmospheres are still dynamic. The presence of a massive planet like Beta Pictoris d, with its complex atmospheric chemistry, suggests that planetary systems can develop in ways we've yet to fully understand. For example, the detection of methane, a molecule that can be both a byproduct of geological activity and a sign of biological processes, raises intriguing questions. While methane on its own does not confirm life, its presence in a planet's atmosphere could indicate conditions that are conducive to the emergence of life. This discovery, therefore, is not just about finding a new planet, it's about expanding our understanding of the diversity of planetary environments in the universe. Moreover, the detection of Beta Pictoris d highlights the importance of studying young planetary systems. These systems are like laboratories, offering a window into the early stages of planetary formation. In the Beta Pictoris system, the debris disk is a remnant of the planet-forming material that once surrounded the star. By studying how this material interacts with planets, astronomers can gain insights into the processes that shape planetary systems. For instance, the presence of a massive planet like Beta Pictoris d could influence the structure of the debris disk, scattering material and shaping the orbits of other planets. This dynamic interplay between planets and their surroundings is a critical factor in determining the long-term stability of a planetary system. Understanding these interactions can help us predict how planets evolve over billions of years, including the potential for habitable worlds to form and persist. The implications of this discovery also reach into the broader search for life beyond Earth. While Beta Pictoris d itself is unlikely to be a candidate for hosting life, the methods used to detect it could be applied to other systems where life might exist. The ability to detect atmospheric signatures of complex molecules like water vapor, methane, and carbon dioxide is a crucial step in identifying planets that could support life. These molecules are not only indicators of a planet's climate but also potential markers of biological activity. For example, the presence of oxygen in a planet's atmosphere, combined with the absence of methane, could suggest the presence of photosynthetic life. Similarly, the detection of certain combinations of gases could point to the existence of microbial life. By refining these techniques, astronomers are building a toolkit that could one day help us answer one of the most profound questions in science: are we alone? But this discovery is not without its challenges. Detecting atmospheric signatures requires extremely sensitive instruments and precise data analysis. The James Webb Telescope, with its advanced spectroscopic capabilities, has been instrumental in overcoming these challenges. Its high-resolution spectrograph can disentangle the faint signals of planetary atmospheres from the overwhelming light of their host stars. This is particularly important in systems like Beta Pictoris, where the debris disk emits its own light, complicating the detection of a planet's atmosphere. The ability to separate these signals is a testament to the power of modern technology and the ingenuity of astronomers. As we continue to refine these techniques, we may uncover more planets that have been hidden in plain sight, further expanding our knowledge of the universe. In the grand tapestry of the cosmos, the discovery of Beta Pictoris d is a thread that weaves together the threads of planetary formation, atmospheric science, and the search for life. It reminds us that the universe is far more complex and diverse than we once imagined. Every new discovery, no matter how small, adds another layer to our understanding of how planets form, how they evolve, and what conditions might make them capable of supporting life. The James Webb Telescope, with its ability to peer through the veil of cosmic dust and reveal the secrets of distant worlds, is a powerful tool in this ongoing quest. As we continue to explore the universe, we are not just finding planets, we are uncovering the intricate processes that shape them, and in doing so, we are getting closer to answering some of the most fundamental questions about our place in the cosmos. For decades, the search for planets beyond our solar system has been a journey of patience, ingenuity, and relentless curiosity. The first confirmed exoplanet, 51 Pegasi b, was discovered in 1995, a gas giant orbiting a Sun-like star in a scorching close orbit. This breakthrough, achieved through the radial velocity method, opened a floodgate of possibilities, revealing that planets are common in the cosmos. But the early days of exoplanet science were marked by limitations. Instruments could only detect massive planets with short orbital periods, and the faint signals of smaller, Earth-like worlds remained elusive. It wasn't until the 2000s, with the launch of NASA's Kepler Space Telescope, that the field transformed. Kepler's transit method, monitoring the dimming of stars as planets passed in front of them, allowed astronomers to catalog thousands of exoplanets, from hot Jupiters to rocky worlds in habitable zones. Yet, even as these discoveries piled up, a fundamental challenge persisted: how to detect planets hidden within the dusty, chaotic environments of young stellar systems. These systems, like Beta Pictoris, were prime targets for planet formation, but their thick disks of cosmic dust obscured direct observations. For years, astronomers relied on indirect methods like measuring a star's wobble or the subtle dimming of light to infer the presence of planets. But these techniques often left questions unanswered. Where were the missing planets? What happened to the ones that formed in these dusty nurseries? The answer, it turns out, lay in the very dust that had once hindered discovery. In the 1980s, infrared observations revealed the existence of a disk around Beta Pictoris, a star only 12 million years old. This disk, composed of gas and dust, was a sign of ongoing planet formation, a dynamic, turbulent environment where planets could be born and hidden. Yet, despite decades of study, the system remained a puzzle. The disk's brightness made it difficult to peer through, and while some suspected planets existed within it, their presence couldn't be confirmed. The challenge was not just technical, it was a matter of perspective. Traditional methods struggled to detect planets in such crowded, dusty systems, where the light from the star overwhelmed the faint signals of their potential companions. But the discovery of Beta Pictoris d, made possible by NASA's James Webb Space Telescope, represents a turning point. It's a testament to how far the field has come and how far it still has to go. To understand this breakthrough, we need to trace the evolution of exoplanet detection. The early days were defined by the limitations of technology. The radial velocity method, which measures a star's wobble caused by gravitational tugs from orbiting planets, was revolutionary. Yet, it could only detect massive planets with short orbital periods, like 51 Pegasi b. Similarly, the transit method, used by Kepler, required planets to cross in front of their stars, making it ideal for finding planets in tight orbits but blind to those in more distant, stable paths. These methods were powerful, but they left gaps. They couldn't account for planets hidden behind dust, or those that formed in the cold, outer regions of a system. Enter the infrared. In the 1990s, astronomers began using infrared wavelengths to peer through the dust of young stellar systems. The James Webb Space Telescope, launched in 2021, builds on this legacy, but its capabilities are far more advanced. Infrared light, with its longer wavelengths, can penetrate the dense clouds of dust that obscure young planets. This allowed scientists to detect the faint heat signatures of planets forming in these disks, even when they're shrouded in darkness. But the detection of Beta Pictoris d isn't just about infrared. It's about the power of spectroscopy, the ability to analyze the light emitted or absorbed by a planet's atmosphere. When Webb's instruments captured the light from Beta Pictoris d, they didn't just see a planet, they saw its atmosphere. By studying the absorption lines in the spectrum, astronomers identified key molecules: carbon monoxide, water vapor, and methane. These fingerprints provided critical clues about the planet's composition, temperature, and even its potential for hosting life. But this wasn't the first time spectroscopy had been used to study exoplanets. For years, astronomers had used this technique to analyze the atmospheres of hot Jupiters, planets so close to their stars that their atmospheres are heated to extreme temperatures. These planets, with their thick, metal-rich atmospheres, offered a glimpse into the conditions of gas giants. However, Beta Pictoris d is different. It's a colder, more distant world, and its atmosphere contains molecules that suggest a different evolutionary path. This discovery highlights how far spectroscopic techniques have come. Early missions like the Hubble Space Telescope could detect broad spectral features, but they lacked the resolution to identify specific molecules. Webb's advanced instruments, with their larger mirrors and more sensitive detectors, allow for precise measurements of atmospheric composition. This is a game changer. It means we can now study not just the existence of exoplanets, but their chemical makeup, their climates, and even their potential for habitability. But the journey to this point wasn't linear. It was marked by setbacks, breakthroughs, and a deepening understanding of the universe. In the 1980s, the first direct images of an exoplanet were captured, but they were blurry, low-resolution glimpses of a faint, distant world. These images, taken by ground-based telescopes, were groundbreaking, but they couldn't reveal much about the planets themselves. The technology to image exoplanets directly was still in its infancy. It wasn't until the 2000s that coronagraphs, devices that block a star's light to reveal fainter objects, were refined enough to capture clearer images. The Spitzer Space Telescope, which operated in the infrared, played a key role in this progress. It allowed astronomers to study the thermal emission of planets, providing insights into their temperatures and compositions. Yet, even with these advances, the detection of planets in dusty systems remained a challenge. The Beta Pictoris system, with its thick disk, was a prime example. For years, scientists suspected that planets existed within it, but the dust made direct observation nearly impossible. The disk's brightness overwhelmed the faint light from any potential planets, making them invisible to traditional methods. It was as if the system was cloaked in a veil of cosmic dust, hiding its secrets from view. But the discovery of Beta Pictoris D shows that this veil can be pierced. The key lies in the combination of advanced instrumentation and innovative techniques. Webb's ability to detect atmospheric signatures is a culmination of decades of research. It builds on the work of earlier missions, but it also represents a leap forward. The telescope's high-resolution spectrographs, capable of analyzing light at unprecedented precision, are a direct result of years of technological development. These instruments can distinguish between the light from a star and the light from a planet, even when the planet is shrouded in dust. This is a critical advancement because it allows astronomers to study planets in environments where they were previously invisible. The implications are profound. If we can detect planets hidden in dusty disks, we can study the early stages of planetary formation. We can learn about the processes that shape gas giants, rocky worlds, and even the conditions that might lead to life. The Beta Pictoris system, with its young age and active disk, is an ideal laboratory for such studies. It's a place where planets are still forming, where the dance of gas and dust is shaping the architecture of a planetary system. By studying Beta Pictoris D, we're not just discovering a new planet, we're gaining insight into the birth of planets in our own solar system and beyond. This discovery also underscores the importance of long-term observation. The Beta Pictoris system has been studied for decades, with each new mission building on the knowledge of the last. The first infrared observations in the 1980s revealed the disk, but it wasn't until the 2000s that astronomers began to suspect the presence of planets. The Hubble Space Telescope, with its ability to capture high-resolution images, provided some clues, but it wasn't enough to confirm the existence of Beta Pictoris D. It was Webb's advanced spectroscopic capabilities that finally unlocked the secret. This highlights a broader trend in astronomy, the power of incremental progress. Each new mission, each new instrument, brings us closer to understanding the universe. The journey to discover Beta Pictoris D was not a single breakthrough but the result of a sustained effort spanning decades. It's a reminder that the search for exoplanets is as much about patience and persistence as it is about technology. And yet, even with all these advances, there are still mysteries to solve. The Beta Pictoris system, for example, is just one of many young stellar systems where planets may be hidden. The question is, how many more are waiting to be discovered? The answer may lie in the continued development of telescopes like Webb, which can peer deeper into the cosmos and uncover planets that have eluded us for years. The discovery of Beta Pictoris D is a milestone, but it's also a beginning. It opens the door to a new era of exoplanet research, where we can study not just the existence of planets, but their atmospheres, their climates, and their potential to support life. As we look to the future, the lessons learned from this discovery will guide the next generation of missions. They will build on the foundations laid by earlier missions, pushing the boundaries of what we can observe and understand. The story of Beta Pictoris D is not just about a single planet, it's about the evolution of a field, the triumph of human curiosity, and the endless pursuit of knowledge. And as we continue to explore the cosmos, we'll find that the universe is full of surprises, waiting to be uncovered by the next generation of scientists and explorers. The discovery of Beta Pictoris D has ignited a wave of excitement in the astronomical community, but it has also raised more questions than answers. For decades, the Beta Pictoris system, a star surrounded by a vast, glowing disk of cosmic dust, has been a focal point for exoplanet hunters. Yet, despite decades of observation, this giant planet had remained hidden, its presence masked by the very dust that made the system so intriguing. Now, the James Webb Space Telescope has revealed its existence through subtle clues in the planet's atmosphere, but the method itself has sparked debate. How can we be certain this is a planet and not some other phenomenon? What does the presence of carbon monoxide, water vapor, and methane tell us about its nature? And if this method works here, could it unlock a new way to find planets in other dusty systems? These are the questions that now drive the search for answers, and they highlight the complexity of what we've just learned. One of the most immediate mysteries revolves around the reliability of the detection method. The team behind the discovery used spectroscopy to analyze the light passing through the dust disk, searching for molecular signatures that might indicate the presence of a planet. Carbon monoxide, water vapor, and methane are all gases that can be found in planetary atmospheres, but they can also be produced by other processes. For instance, the dust disk itself might emit or absorb these molecules in ways that mimic the signature of a planet. Some scientists are cautious about interpreting these signals as definitive proof of a planet, arguing that the data could be influenced by factors like the disk's temperature, density, or even the star's own emissions. Without direct imaging or additional data to corroborate the findings, the existence of Beta Pictoris d remains a tantalizing possibility rather than an absolute certainty. This uncertainty underscores the challenges of studying exoplanets in systems like Beta Pict, where dust and light make direct observation difficult. Even if the planet's existence is confirmed, its characteristics remain shrouded in mystery. The spectral analysis suggests it's a massive gas giant, but how massive? What is its temperature, and how does its atmosphere compare to those of other known exoplanets? The presence of methane and water vapor, for example, could indicate a complex chemistry at play, but these molecules can also be influenced by the planet's distance from its star and the radiation it receives. If Beta Pictoris d is orbiting far from its star, its atmosphere might be colder and denser, while a closer orbit could lead to different chemical reactions. However, the exact location of the planet within the dust disk is still unclear. Is it nestled within the inner regions, where the star's light would make it harder to detect, or is it farther out, where the dust might be less dense? These details are critical for understanding the planet's formation and evolution, yet they remain elusive. Another layer of uncertainty lies in the broader implications of this discovery. The Beta Pictoris system is one of the most studied in our galaxy, yet this planet's existence challenges existing models of planetary formation. Traditionally, gas giants are thought to form in the cold, outer regions of a star system, where icy materials can condense into solid cores. However, Beta Pictoris d appears to be in a region where such conditions might not be ideal. If the planet is indeed hiding within the dust disk, its formation could involve processes that are not yet fully understood. Some scientists speculate that it might have formed through a different mechanism, such as gravitational instability, where a clump of gas and dust collapses directly into a planet without needing a solid core. Others argue that the planet could have migrated from a different region of the system, complicating the picture of how planetary systems evolve. These possibilities highlight the gaps in our knowledge and the need for further observations to refine our theories. The discovery also raises questions about the role of dust in planetary systems. The Beta Pictoris disk is not just a backdrop, it's an active environment where material is constantly being stirred, accreted, and potentially reshaped by the gravitational influence of unseen planets. If a planet like Beta Pictoris d exists, it could be influencing the disk's structure in ways we haven't yet measured. For instance, the planet's gravity might be shaping the dust into spiral patterns or creating gaps in the disk, but these features are difficult to detect without direct imaging. Moreover, the dust itself could be a double-edged sword. While it obscures planets, it also provides a unique opportunity to study how planets interact with their environments. The presence of methane and water vapor in the disk's atmosphere suggests that the dust is not just a passive medium but an active participant in chemical processes that might be relevant to planetary formation. However, the exact mechanisms at play remain unclear, and further research is needed to unravel them. Perhaps the most profound mystery lies in the implications for the search for life beyond our solar system. While Beta Pictoris d is a gas giant, its atmosphere could harbor complex chemistry that hints at the potential for life in other planetary systems. The presence of water vapor, for example, is a key ingredient for life as we know it, and methane could indicate ongoing geological or atmospheric activity. However, these molecules alone do not confirm the presence of life, and their detection in a gas giant's atmosphere raises questions about how they form and persist. Are they the result of volcanic activity, chemical reactions in the atmosphere, or even the influence of the star's radiation? Understanding these processes could provide insights into the conditions necessary for life, but they also highlight the limitations of our current methods. The James Webb Telescope's ability to detect such molecules is groundbreaking, but it's only the beginning of a much longer journey to decipher the chemical signatures of exoplanets. The scientific community is now grappling with the implications of this discovery for the future of exoplanet research. If the method used to detect Beta Pictoris d proves reliable, it could revolutionize how we search for planets in dusty systems. Traditional methods like radial velocity and transit photometry are limited by their reliance on direct light from the planet or the star's wobble, making them ineffective in systems where dust obscures the view. Spectroscopy, on the other hand, offers a way to peer through the dust and detect atmospheric signatures, opening up new possibilities for studying planets in environments that were previously inaccessible. However, this method is still in its infancy, and its accuracy depends on the quality of the data and the ability to distinguish planetary signals from other sources. Scientists are already working to refine the technique, testing it on other systems to see if it can be applied more broadly. Despite the uncertainties, the discovery of Beta Pictoris d has already sparked a new era of curiosity and exploration. It reminds us that the universe is full of surprises, and that even the most well-studied systems can hold secrets waiting to be uncovered. The planet's existence, whether confirmed or not, has already pushed the boundaries of what we know about planetary formation and the tools we use to study it. As scientists continue to analyze the data and refine their methods, they are not just solving puzzles, they are laying the groundwork for future discoveries. The questions raised by this discovery are not just about Beta Pictoris d, they are about the nature of planets, the chemistry of their atmospheres, and the methods we use to explore the cosmos. In the end, the search for answers is as much about the journey as it is about the destination, and that journey is only just beginning. A giant planet had been hiding inside one of astronomy's most closely studied planetary systems, concealed by a bright disk of cosmic dust. Webb revealed Beta Pictoris d through atmospheric traces of carbon monoxide, water vapor, and methane, showcasing a promising new method for finding elusive exoplanets. This part of our deep dive into NASA's Webb telescope discovers giant planet hiding in one of astronomy's most famous systems focuses on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Today, we're diving into a discovery that redefines how we hunt for planets beyond our solar system. For decades, astronomers have studied the Beta Pictoris system, a star just 63 light-years away, famous for its swirling disk of dust and gas. This disk, glowing with the light of young planets, has long been a cosmic laboratory for understanding planet formation. But something was always missing: a massive planet hiding in plain sight. Until now. NASA's James Webb Space Telescope, with its unprecedented ability to peer through cosmic dust, has uncovered a giant planet, Beta Pictoris d, concealed within this disk. This isn't just a find, it's a breakthrough in how we detect worlds that were previously invisible. The key? Webb didn't see the planet directly. Instead, it analyzed the faint fingerprints of its atmosphere. By measuring traces of carbon monoxide, water vapor, and methane in the starlight, scientists pieced together the planet's existence. These gases, trapped in the planet's atmosphere, acted like a cosmic beacon, revealing its presence despite the dust cloud that had cloaked it for years. This method is revolutionary. For years, exoplanets have been found using techniques like radial velocity or transit, which rely on the star's wobble or the planet passing in front of it. But these methods struggle with dusty systems like Beta Pictoris. Webb's approach, detecting atmospheric signatures, opens a new door. It means we can now search for planets in environments once thought too chaotic or obscured. Beta Pictoris d itself is a marvel. Estimated to be about 10 times the mass of Jupiter, it orbits its star at a distance where temperatures are frigid enough for methane to persist. Its atmosphere, rich in these gases, suggests it's a young world still cooling from its formation. This discovery isn't just about one planet. It's about the future of exoplanet science. By studying such worlds, we learn how planets form, how they evolve, and what conditions might support life. But the implications go deeper. If a planet hidden in dust can be found, what other planets are waiting to be discovered? How many of the so-called missing planets in our galaxy are simply cloaked by dust, unseen until now? The Webb telescope's ability to detect atmospheric signatures means we're no longer limited by the visibility of a planet. We can now probe the chemistry of distant worlds, even those shrouded in mystery. This discovery also highlights the importance of long-term observation. Beta Pictoris has been studied for decades, yet this planet remained hidden. It took a new generation of technology and a fresh approach to reveal it. The lesson is clear: the universe is full of surprises, and our tools are only getting better. For astronomers, this is a triumph. For the public, it's a reminder that the cosmos is still full of mysteries waiting to be solved. And while this discovery is a milestone, it's just the beginning. The James Webb Space Telescope is already turning up more surprises, from ancient galaxies to the atmospheres of rocky exoplanets. Each finding brings us closer to answering the question that has driven humanity for millennia: are we alone? As we continue to explore, one thing is certain: every new discovery challenges our understanding and sparks new questions. So if you've enjoyed this deep dive, hit that subscribe button to join us for more journeys into the unknown. And if you have your own theory or question about this discovery, drop it in the comments. The universe is full of secrets, and together, we're learning to read them.